This is practice A for section 7.3. We're going to look at numbers 5 through 7. We're going to find the length of the altitude to the hypotenuse. That's this piece. This piece. We'll call it x. That's what we're looking for. Round your decimal answers to the nearest tenth. You could do nearest hundredth. We usually do that as well. We did this exact same problem in the lesson. I am almost positive that this altitude to the hypotenuse is 2.4. What you need to do is split your right triangles apart, just like we did in this previous exercise. Put the lengths on that you're aware of, and since they're all similar, you can write a proportion. I think in the lesson I compared this triangle with this triangle. Since I know all three of these sides, I can compare this triangle with either of these. So maybe this time I'll compare this one with this one, and you should get the same answer at 2.4. So let's compare short leg to short leg, x to 3. That ratio, short leg to short leg, is the same as the ratio of hypotenuse to hypotenuse, 4 to 5. Now, when you cross multiply, you better get 2.4. 5 times x is 5x, and 3 times 4 is 12. 12 divided by 5 is 2.4. That's how that works. Now, I remembered this because I made a point to tell you when you have a 3, 4, 5 right triangle, the next time they ask you for the altitude of the hypotenuse, it's not going to change. It's going to be the same length every single time. Okay, now we have new triples over here, 8, 15, 17. So whenever we solve for this, whatever this is, will work for every single right triangle where it's 8, 15, 17 for the lengths. Okay, so let's split these up. Little right triangle, medium, big. Now on my big, I know I got 8, 15, 17, and that's the triangle I'm going to compare to one of these. Okay, now just for practice, here's your little one. This altitude to the hypotenuse, that's your long leg. The hypotenuse over here is 8. On your medium-sized right triangle, that altitude to the hypotenuse is the short leg, and then your long leg is, wait a minute here, oh, this is 17. Okay, so this 17 is this whole entire length. Don't think that it's this one. This is your hypotenuse on the medium-sized right triangle, that's 15. Okay, so you can compare this triangle with either of these two, totally up to you which one you do. Maybe we'll do the small one since we did the medium one there. We're going to compare x, that's the long leg, with 15, that's the long leg here. That's the same thing as hypotenuse to hypotenuse. And then we're going to cross multiply. 17 times x is 17x. 15 times 8, I'm just going to type that in the calculator. That gives me 120. Now I need to divide that by 17 to figure out what x is. Okay, so if I'm rounding to the nearest hundredth like I like to do, I would call it 7.06 because that digit is 5 or above. So the next time you are asked to solve for the altitude to the hypotenuse of an 8, 15, 17 right triangle, hopefully you remember that you've done this before. It's always going to be 7.06. Rounded, of course. That's the exact answer. This is what we're going to round it to. Number 7 is multiple choice. We're going to use the diagram at the right. Which proportion is true? Well, we talked about geometric means. This altitude to the hypotenuse is a geometric mean of the two pieces of the hypotenuse. So remember we made the geometric mean red. That's segment DB. It's the geometric mean of the two pieces, green and blue, segment AB and segment BC. These ones don't work. We have segment AD, which is a leg, as a geometric mean, which is fine. But it needs to be the geometric mean of the piece of the hypotenuse it touches, which is segment AB, which is good so far, and the whole entire hypotenuse, segment AC. So if this was to be true, you would need segment AC down here. Okay, this one, segment AB, that's the geometric mean in this one. We don't have a geometric mean theorem where that little piece is the geometric mean, so this guy just doesn't make any sense. But that's a geometric mean theorem for the altitude to the hypotenuse, and we use that one a lot.